This video is going to be a capture the flag video write-up of a challenge from the Google CTF Finals 2019. So this was recorded quite a while ago. The challenge is a hardware challenge. It's ultimately a FPGA bitstream reversing challenge, but it also has a GPU component to it and a Rust component to it, and it's a very interesting type of software. And I had a chance to sit down with the challenge author to talk about the software, how it was created, and what went into it. And I also had a chance to talk to Gynvael, who you hopefully know from his excellent YouTube channel, who also does crazy security streams and videos. And Gynvael was testing the challenge, so it's very interesting to hear his approach when trying to solve it. The interview is quite long, as you can see in the minutes of the video, but I think it's a very interesting conversation. The CTF challenge is of course interesting in itself, but I think there's just so much more around it that you can learn by just listening to the author or Gynvael describing certain problems and how they approached them. I personally get really a lot out of just people talking about the stuff they are doing, and it's not super condensed, but I still think it's very, very interesting and insightful. So I hope you enjoy this style of video and let me know if I should do something like this in the future again. So you are the author of the GPURTL challenge?
Yes. Yes, I am.
So the name includes GPU, which I assume has something maybe to do with shaders or GPU code. And then we have RTL, which might be related to transistor logic, maybe?
Yeah, very good. RTL specifically stands for register transfer level in this particular context, which is relevant usually when doing FPGA design, which was the inspiration for this challenge. My general goal with the challenge was to try and develop something that a traditional disassembler just can't deal with.
Okay.
And I've done a bit of hardware design on FPGAs before, and so I know how difficult it is to debug what FPGAs are doing, and there's whole suites of proprietary tools that do this. And so I thought it'd be pretty cool to go down that route and make something that looks a little bit like an FPGA. In fact, what I wanted, the goal was to have a reusable thing that could simulate FPGA designs, any FPGA design. I wanted to actually make it a useful tool beyond just the CTF, and then make a CTF challenge out of it as well.
All right.
And all of this running on a GPU because, yay, it's more difficult. Also parallelism. I mean, FPGAs are indeed parallel devices.
And that works out with the way the shaders are set up, that it can in parallel?
Yes, so it runs everything in parallel, which didn't come without its fair share of issues, which I can talk about later.
I can imagine, yeah. So, Gynvael, I believe, has done the test run of this.
Yes.
And he showed me a part of how he kind of approached this challenge with a weird setup. So I'm very curious now to see kind of the other side of this.
Okay, so he probably showed you the big graphic, which showed how various things were connected, and you can see the various blocks in the program.
No, he didn't. So he showed me kind of it was very colorful, and it was and on one axis was the time, and each clock cycle was thing there, and then he printed the register outputs of each LUT.
Yep.
And color coded how far they are away from the output. It looked crazy, but there were some interesting insights from that.
Do you synchronize it with a clap or something? Well, now you have a clap, you can synchronize it.
Perfect.
Yeah, so this is a picture from when I solved the challenge, and you can tell me what the challenge is about by looking at this picture.
Okay, wait. So the challenge that you download, is that a regular binary to run?
Okay, that's a good question. You get a binary, you get a binary file which you have no idea what the format is and what is it about, and you get a Lua script.
Okay.
And the Lua script has keywords like inputs, outputs, and correct output, and pin numbers. And yeah, that's basically what you get. And this is a picture I got when I was close to solving the challenge.
Okay, wow, okay. Okay, couple of guesses. Could be a memory dump of some sort, but there are also lines, so it could be a time diagram of if you say pins high and low. I'm trying to see like there are some variations in those. So I don't know, is this zoomable or is this already a perfect?
This is the
Yeah,
after.
yeah.
It's quite long actually.
Okay, but that there are different colors. So that's why I thought it might be memory, and the different colors just define like certain different values of it.
Cool. I think you're super close actually. So to keep you from guessing, the challenge was basically an FPGA simulator implemented with Rust and GPU, so in shaders basically. And what you get, the binary file, is the bitstream for this FPGA. And the FPGA has over 2000 lookup tables, or like logic cells, whatever you want to call them. And each one has basically 4 inputs, then a lookup table, 2 outputs, actually 1 output, which is a normal output, and the other is a register, like flip-flop output. And what you see here on this image is basically the register values from all the gates. So there would be, there isn't 2000, over 2000 here because it's already only the part relevant to actually the solution. Diagram is like this because I have absolutely no idea how to solve this kind of challenges. And this is the second time I solved a challenge like this, and the first time I used a similar method. And yeah, and this time I also ended up using this method. And it's actually pretty good because you can, on this picture, if you know what to look for, you can deduce the actual algorithm which is implemented inside the bitstream. And from that, it's pretty close to get a solution of a challenge.
Can you say again, what is it? What are the axes again?
Okay, so this is time, the Y is time, the vertical is time. The horizontal large blocks, they are I think 32 pixels high, are a cycle, like a clock cycle in FPGA, and each line inside the cycle is a microcycle, which is basically propagation from one register to the other, as in one gate calculated already the result, and the result propagates to another gate which is connected, and another, and another, and another, and at some point they stabilize for the cycle, and that's what the last line basically in which cycle tells you.
Wait, okay, I don't get, like, wait, are these now different gates encoded in there, or
each
pixel
column,
line?
each pixel is one gate or one register. But it's actually the register which is at the end of the gate.
Yeah, okay.
Yeah.
Okay. And so these changes here, so when it's like on or off, it's just like
lighter or darker.
And this was time, so it was like on and then turned off at some point, and this was on.
Yeah.
And what does the color represent?
The color represents the distance from the output, meaning the purple ones being the output, and this is distance 1 from the output, distance 2, distance 3, and so on. So this is basically all connected to the output pins, and these ones are next to it, and so on and so forth. So these one, for example, the orange ones are really deep inside the network, looking from the output side.
Is there a particular reason why you didn't sort it for exactly that?
So it's also sorted by the pin number, and the reason I didn't sort it was because I wanted to have easily be able to figure out which pin is it.
Okay. Because you are searching for a particular pin.
Yeah, I'm basically
the output pin, or is there like a single output bit at the end?
Actually, there, as you can see how many outputs there are by the size of this, right? So there are, I think, 256 or 128 outputs, something like that. Okay, so basically to restart about the challenge, right? It's like this. You get the FPGA simulator, right? The first thing you have to do, you have to figure out it's an actual FPGA simulator. Then you have to figure out how does it simulate the FPGA and what is the bitstream format in the file. Once you have that, which is actually the one part is reverse engineering Rust binary, the other part is reverse engineering compiled shaders. And then you get the bitstream, which after you can decode it and you know it's actually like the lookup tables and how they are connected, you approach the real challenge, which is figure out what does it do. You know there is an input, and you know the input is basically the flag split into bits, right? And you know the output is going to be some value, which is 256 bits long or something like that, right? And you have the correct output at the end, which you have to arrive at. for the charge to tell you succeeded.
And it's definitely not just a Boolean logic, because you were also interested in the cycles and that there's an algorithm implemented. So it's not as easy as doing some correlation of like flipping input bits and seeing what happens.
Exactly. And in honesty, I have absolutely no idea how to reverse a bitstream. So this was a learning experience for me. Yeah.
So to get the data that you used for this graph, did you had to instrument the simulator to...
Excellent question. I actually had to re-implement it in Python.
Okay.
So yeah, and I've written a lot of code in Python to dump different things, to get the graph of how the gates are connected, to try to reason on that, to get the lookup tables, to try to convert a lookup table back into a Boolean logic function, or like set of if-else statements or tree of if-else statements. And based on that, based on looking at this colorful picture and another colorful picture which I can show you, it only shows the cycles. There are no microcycles here. So you can see that in this output column, right, the color encoding is identical. You can see that first it does something weird with the first 64 bits, then second 64 bits, and so on. So it tells you basically how is the input processed and how is the output processed, and you know that is 64-bit blocks, right? You know there are 4 rounds. And you can see how many cycles one round takes. And you would find out that it's actually 32 cycles. And based on that information, if you actually put what I already told you in Google, like 64 bits, 32 rounds, 32-bit variables, you get the name of the algorithm which is used here. It's a cryptographic algorithm, an encryption actually. And based on that, you can do basically a known plain text attack to get the key and then be able to reverse it and get the flag. 24 hours, that's how long it took me to test it while learning. I'm pretty sure people who actually know what to do in this case would have it easier.
Color-coded how far they are away from the output. It looked crazy, but there were some interesting insights from that.
Well, that's actually an awesome way. So that answers my question I had to him about that, because I didn't understand it particularly well either. But yes, that is actually one way, if you're doing FPGA design, how you would approach sort of debugging an FPGA is looking at how the values progress through a system like that. And visualizing it as a colorful graph is a really good way of doing it. But yeah, let me show you the other side of the coin. So more of the source code level stuff. Let's see. So this is the actual source code for the project. So what the challenges are actually given is a binary called GPURTL, and then 2 additional files, ctf.bin and ctf.lua. And what they look like, and I'm going to totally spoil it with the file names here, but yeah, so t.bin and t.lua are the original file names. So this is what the Lua script looks like for starters. There's a bunch of variables, it's just addresses really. And then the main logic is in this execute function, which from what the challenger can see appears to write some input bytes to some bits, which was defined further up, along with the input. Oh, and you can see the solution here. It then runs a bunch of iterations until it is done, and it measures doneness by reading an output bit. There's also a check to make sure that we're not hitting a bug, because that occasionally did happen. And then we read the output and check is it what we expected or not.
Are these bugs related to, are you simulating also the hardware behavior of like rising edges slowly and that might glitch or so?
Yes, so the basic idea was that in order to try and make the performance better, I cut a lot of corners in terms of the correctness of the implementation, which on the Intel GPU of my laptop works fine. On the NVIDIA GPU of my workstation did not work fine. And so hence why I now have that check for convergence failure. But that the current version of the challenge and the one that the challengers are solving does not hit that bug on either platform 100% of the time. So it is a correct, albeit slow implementation. Plenty of chance for optimizations. But yes, so this is generally what happens. And as you can see, that is indeed the correct input to make it work. And then this is the bitstream, yes. At the top of the file, you have GPURTL, then PC, which I can't quite remember what those those values mean. And then you have what appears to be 4 bits, and it's an 8. Then there's some other metadata, and then you get this block, which all looks very similar, or the CA008. And it's fairly obvious, hopefully, that they're in blocks of 4 bytes, so 32 bits. And that becomes quite important because, is it 32 bits or 64 bits? I can't quite remember. We'll look at the source code in a moment. This is the programming for the lookup tables that are being simulated on the GPU. So this is actually generated code from a hardware description.
Does this look similar to other bit streams of actual like commercial FPGAs? Like obviously you didn't implement everything, but like is it similar? Like what I'm asking is, could somebody who is experienced with FPGA reversing could maybe or kind of recognize a little bit already of it?
Quite possibly. I haven't really looked into detail of how commercial FPGA bit streams look like, but I was basing it on the model of you synthesize your design and then generate a bit stream. This happens to be what the GPURTL bit stream looks like. Okay. But it should, in theory, be very similar to commercial FPGAs as well, in that we are programming a bunch of lookup tables, which is encoded in this logic, and then we are specifying, so while a typical FPGA specifies how wiring is, how each crossing of wires has a programming bit associated with it on an FPGA. That doesn't really make sense here, so instead we have addressing. And I'll show you how that works when we have a look at the shader. But it's basically the same pattern all the way down until the very end, where somewhere along here, and I believe it sort of starts here, we then have the jump table. So this was to implement long jumps across the memory of the GPU. Which you'll see why that's relevant when we look at the shader. I think the right thing to do now is actually have a look at what the shader looks like before it gets compiled into horrendous whatever it is. So it's this. So this is what the shader looks like. We get some programming, which is 64 bits, so I'm slightly wrong there. We've got a data buffer, we have the programming buffer, and we have a jumps buffer. Just as I explained, comes directly from the binary input. We've then got some constants, but they're not particularly relevant here. And what we do in the main function is we unpack the programming at an index which is defined by the current iteration. We then, for a bunch of cycles, do this lookup operation, storing the result back into the data buffer every time. And then we've got some memory barriers in an attempt to make it converge better, but turns out they didn't really work, so we had to do something else. And then the last bit is a copy into the register when there is a rising clock thing mentioned.
Okay. I've never written shade. I have written a little bit of shader in computer graphics class, and there wasn't. I don't remember there was like a main function. It was. I feel like it looked differently to that.
So, if you're writing graphics code on a GPU, you're writing a vertex shader and a fragment shader, typically. And what those will do is they will take a buffer of vertices and manipulate them in some way. And the fragment shader will take a fragment and manipulate them in some way. And manipulation is things like calculating the color of a fragment, or moving a vertex, or applying texture coordinates, things like that. This is a compute shader. And compute shaders are the most generic form of shader. They just have a main function, and then they do stuff. And so you specify work groups. That's sort of what the overall layout of the shader looks like.
Is a shader program, a compute shader like this, executed on each GPU core? Is this like, do you have to think about this in massive parallelism of this program?
Exactly. So this is this shader, or this block of code, runs in parallel on every compute unit on the GPU. And that's really why GPUs are suited for this kind of task, because each element that needs to be calculated is independent from the others.
Okay. Now my only confusion is left is with the orchestration. Like, how do you tell which one should calculate which part of the...
Right. So that all comes through these index. I've defined them as macros here because I was lazy. But so if we have a look at config index, which is defined up here, it is the global invocation ID.y times the workgroup size in X plus the X global invocation ID. What this effectively means is you get a number from 0 up to the size of the data buffer, because that's the way that I've programmed it. And so that is the index that this particular GPU is working on. And the GPU will execute one of these kernels for every one of the numbers, every one of the so-called work units, defined by work groups, which is how compute shaders work.
All right.
So what I've actually defined at the top of the file is that you've got a local size of 256, which corresponds to the block size in the binary file, and then we increment the global y for every block. Okay. So that's why that particular expression makes sense in this case. I could have also done it in X, but I didn't. So then the LUT index, there is an offset, and then you have twice the config index. Why 2 times the config index? Because every cell is actually made up of 2 values, a register and a LUT. And the LUT one changes every cycle. It gets updated every single time. The register one only gets updated when there is a rising clock in order to try and simulate how hardware would work. Obviously, this is an oversimplification of hardware, but it worked for the challenge. Yeah. So then we look at the lookup function, which so it looks at a bunch of places in the data buffer, pulls them out, and we use the 4 bits that we have selected from places in memory to select one of those 16 bits, and that then gets written into the as the data value, which is very similar to how FPGA LUTs work. And then there is some special stuff in getBitAddress to deal with jumps. So the basic idea was that the majority of lookups from a LUT will be local. They will be very close to the local cell, and so we should optimize for that case. And so if the value is less than 0x800, then we assume it is defined as a relative lookup. So it's actually relative to 400 is the current value. Anything higher than 400 is to the increasing memory locations. Anything less than 400 is lower. And that's where you see the LUT index line.
So this is just code speed optimization. This has nothing
code
to do with
size optimization more than anything. So unfortunately,
so you don't have to use a full address. Just
yes. So I don't need a jump, a full 32-bit jump address for every single bit of every single LUT.
Okay.
I only need them for the ones that are jumping across lots of memory.
Yeah.
I don't know how much of a difference this makes. It probably actually slows down the program, but it was something that I decided to implement. So that's how the shader works.
And this is what they don't get the source code, but they have the compiled shader, and they need to reverse engineer the shader.
So this shader is compiled into SpearV, which is the Vulkan intermediate representation of shaders. I actually don't know what that looks like, but it is reversible. It's designed, there's nothing special about it. It's a standard compilation step. You do need to understand SpearV to understand what this is doing there.
Yeah. Okay, and based on reversing this, they will understand what the data, the bitstream will...
Yes.
Or at least how it is set up.
Yes, so understanding how this shader works directly influences how to understand that bitstream. Yeah. Now I think it's probably a good time to actually look at the GPURTL binary itself. The binary is written in Rust, and it was compiled with in release mode, but otherwise there was no special obfuscation going on. The reversing of the Rust binary was meant to be not easy, but at least straightforward. It's not meant to be the majority of the challenge. Turns out that reversing Rust is quite difficult, but it's still not the exciting bit of the challenge. The exciting bit is the bitstream reversal. So I can probably show you some of the source code. There's not much that's interesting in it.
Is it just the APIs for the graphics to set up the GPUs basically, and then just, I don't know, is that like shared memory for the GPU to get the bitstream.
Exactly that. It's just a lot of setup and glue code, really. So here you see that this is sort of the high-level implementation of the simulation. So we set up a bunch of buffers. We then set up this iteration, which copies the input ports, runs a bunch of cycles, copies the output. That's one iteration. And then we pass all of this into Lua, and then let the Lua script execute it. And so this is, again, just glue code to get the Lua thing working. And then these are the methods that are available from the Lua code itself. So we saw them before: read output bytes, read output bit, write input bytes, write input bit, the current iteration count, and run an iteration. Very straightforward. I could show you the GPU code as well. This is the sort of low-level Vulkan programming. It's not particularly nice. It's mostly just...
I assume you could get this almost as a template.
Yeah, pretty much. This is just a lot of glue. And remember, I was writing all of this to try and be as generic as possible. I want this to be a useful thing in the future as well.
Okay.
I don't just want it to be for the challenge. And so at some point I hope to open source it, which would be nice. Well, I mean, I guess if this goes live on YouTube, then people can already take it.
What's the license? Should I mention?
So there's nothing particularly exciting here. It's just a lot of glue code, really.
Yeah.
So that's the binary. And hopefully once teams have looked at the binary and worked out how it works and have seen that shader and reversed the shader, they can start to understand the bitstream. And then they will perhaps want to write some sort of decompiler of the bitstream to turn it into a sort of a model of netlist of some kind, at which point it becomes an FPGA challenge instead of a gross GPURTL challenge. At that point, you just need to reverse the hardware, I guess.
Yeah.
But one thing that's really cool, and one thing that, or at least one thing that I find to be really cool, that challengers will never see, is the code that took the Verilog and turned it into the bitstream. And I'm very proud of this code. It's not complete yet, but it's all of this stuff in the synth directory.
I thought you were about to say that you're glad that they don't see it because it's so embarrassing and ugly, but no, you're proud of it.
No, I'm very proud of it. It was fairly difficult code. So let's have a look at t.v. So this is the actual Verilog that generates the bitstream for the challenge. So you've got a top-level module, takes an input plain text and a clock, outputs the ciphertext, and done. And it's got some wires. Anybody who understands Verilog will know what this does. And then there's the module itself, which is this, and then there's some state tracking. The rest is fairly generic code. In particular, you may notice this line here.
Is that the key?
That is the key for the encryption algorithm, which, if a team is paying attention and is good at bitstream reversing, they should be able to figure out that there is this ASCII key being used, because this code isn't very well optimized.
So Gynvael told me he tried to find the key somewhere, but he couldn't find it at all. Do you believe it should be in the compiled bitstream recognizable?
So it might not be very easily recognizable, but it should. There will be constants used, and that may be hidden as LUT programming.
Yeah.
So it may not be immediately obvious. I don't know.
Yeah.
It might be obvious. It might not be.
But you said you do your code directly takes this Verilog code and turns it into a bitstream?
Yes.
Do you apply any kind of optimizations?
There are some optimizations run by the tooling that I use, which is Yosis.
Okay.
Which is a synthesis tool.
Okay, because I was with Gynvael earlier theorizing that maybe there's some compiler step that sees that those are constants and just like really ugly puts it somewhere.
It's quite possible that happens, which makes me a bit sad because it would be nice to have the string pop out at some point. But it's also the kind of thing which you would only find at the end of the challenge.
Yeah.
Maybe this should be an extra challenge for the challengers. Find out what the key to this algorithm was.
Yeah.
Which is quite amusing.
Yeah, you could have turned that into a second reversing for it.
A second reverse, yeah. But that is indeed the key, and it does sort of give you a hint as to which algorithm is in use. And it's the TEA, Tiny Encryption Algorithm.
Ah, okay.
Which I chose because this is the encryption algorithm. It is those two lines, which was very nice. Observing that this bitstream appears to encrypt things in 64-bit blocks and appears to have a very simple, small state, they may very quickly understand that it's an encryption algorithm. And a little bit of research will lead to the tiny encryption algorithm. So that is a totally viable way of solving the challenge, as just recognizing that it is an encryption algorithm with a very simple step. But you still need the key, and that will be the difficult bit. Now, that actually leads to a very good point. As soon as a challenger has realized the tiny encryption algorithm, then they know somewhere within this encryption algorithm there is a key, and they know what the key will look like. So they can actually reverse the bitstream to figure out what the key was. And as soon as they have the key, they don't need to care about any of this code anymore. They can just use the C implementation, which is available on Wikipedia, and do everything on the CPU at that point. That's a totally viable way of breaking this challenge, and one that I wanted to make sure was still available.
Do you see the different kind of options for other kind of side channel ways of looking at this? So Gynvael was re-implementing the whole thing in Python. But I don't know.
I think, yeah, so a re-implementation of the shader component is a very good way of getting introspection into what the code is doing. Because code running on the GPU is typically very difficult to access. However, I did provide the Lua interface as a very easy way of sort of manipulating what's going on. So I expect some teams will be writing crazy things in Lua that like dumps the entire state of the memory every cycle and works out what goes on. In terms of side channels, I'm not sure. I don't imagine there are any timing side channels. I just imagine looking at the structure.
But the Lua script is the trigger for each cycle that is executed?
Yes.
Okay, and so that's what you're saying, they can get the GPU memory or what's going on? Yeah, one could imagine that there might be some side channel attacks in that way by, I don't know. Yeah,
you could very quickly see the structure of what the encryption algorithm is doing every clock cycle. And that isn't totally intended. It should be possible to recognize the encryption algorithm, recognize the block length, recognize the operations in use, and from that work out the encryption algorithm. Because it's a well-known encryption algorithm. It's not something that you need special knowledge to have to figure out.
Okay.
So that's what the Verilog looks like.
And
then the really cool bit is the synthesis tool. What the Makefile does is it takes the Verilog initially, runs it through Yosis, which is a synthesis tool for FPGAs. Yosis then optimizes the entire netlist, turns it into... so remember the Verilog code has things like multiplies, XORs, additions, all of this sort of stuff. Yosis turns it into lookup tables and registers only, which is great because that's what I implement. At which point it writes it out as a blif file. I then take that blif file and generate the bitstream from that with custom code, custom Python code, as you can see in the second step. Then I can quickly show you what the synth code actually looks like. Is place the interesting one? No, place is just the top level. So what I did is wrote a bunch of code that takes the blif file and turns it into a Python representation of registers and lookup tables, along with where the variables came from, and then can also spit that back out as a bitstream. So that's how all of this works. And also it had to calculate the jump addressing, because that's the primary goal of this program, is to calculate what the jump address actually has to be. Is it relative? Is it a long jump, etc.? The main idea of this, and this is one thing I didn't get to implement in the end, is, and you can see it here, annealing. I wanted to be able to take the blif file and then optimize the layout of the lookup tables in order to reduce the number of jumps required, because that shortens the length of the program.
Yeah.
But I couldn't quite get it to work in time, so you have the unoptimized version instead, which is a little bit more homogeneous and easier to read. But that's how that bit of programming worked. And it does indeed work. Well, the annealing doesn't, but the rest does.
Crazy. Is your plan to kind of get it to like a level where, I mean, it can already run pretty much any FPGA Verilog file?
Yep. Any standard Verilog, it should be able to spit out.
Do you think with especially running it on GPU is actually, it's probably much faster than simulating on a CPU? I mean, modern algorithms.
With optimization, yes, definitely. It should be. The architecture is a lot more amicable to running this sort of computation.
Yeah.
The one thing, actually this is probably a good time to talk about it, the one thing that came up as being a problem time and time again was convergence.
Okay.
Because on an FPGA, you have sort of the guarantee that when a clock cycle has rolled through the FPGA, every register has changed approximately at the same time. What this means is that the updated values that the lookup tables on the FPGA are calculating will all become available a fixed time after that clock cycle. This is what timing analysis does. With a GPU, you have no guarantees about which work group runs when.
Okay.
You saw a couple of memory barriers. The thing you didn't see was the changes I actually had to make to the Vulkan implementation. I have raised bugs to put pipeline barriers in the right place. What that means is that the GPU actually has to stall, finish all of its work, hand back to the CPU before it can start the next cycle. And that is slow. You don't want GPUs doing that, but there's no way of getting it to work correctly otherwise.
Okay, and it doesn't. So do all the compute instances share also one? Is all the memory shared?
Yes, memory is all shared.
And you can't like implement some kind of like mutex through that where every compute instance has to raise a bit that they are ready or so?
Nope, can't do it. Because on Intel that would probably work just fine because of, or at least the Intel open source drivers on Linux on this particular machine, it would probably work fine. But it seems that NVIDIA is a lot more happy about running one workgroup to completion. So what it would do is it would run the first workgroup. This is speculation, by the way. Yeah. It would perhaps run the first workgroup, and which would wait on this mutex, and it would just sit there waiting forever because it would never schedule the others. And that's a totally valid execution model. Yay, concurrency. But yeah, so there's plenty of optimization that can be done, I'm sure.
Yeah.
And I imagine that it would become quite a useful tool for simulating large hardware designs, because that is a significant problem when simulating FPGA designs, is that the CPU, it's a serial processor. It doesn't have many cores. It's difficult to simulate things like that. But you then have concurrency guarantees on a CPU that you don't get on a GPU. Yeah. So there are trade-offs, and I'd really like to see this project become a useful tool in the world of hardware design. But we'll see. Yeah. I would love to be able to spend some time on it, some proper time. Yeah. But as a sort of 20% project here at Google, I think that there's a limit to how much time I can spend on this.
Yeah, but that's interesting. That's an exciting project. I really hope that teams will solve it at some point too.
Yes, I hope that.
And hopefully they can also talk about it and it wasn't a remote player or so. Yeah, thank you so much.
Anything else you need from me?
No, that was great.
Cool.
Okay. So the challenge was solved by one team, and you had a chance to talk to them. So how did it go for that team?
So the one team that managed to solve GPURTL proceeded just about how I would have expected them to at the beginning. They disassembled the binary, they pulled out the shader code and ran it through a disassembler, which actually, funny enough, gave them GLSL code very similar to the source code, which I'm impressed by the disassembler that they used. And then they quite quickly worked out that it was running this shader on a sort of data buffer. they actually decided to implement a simulator in Python so that they could introspect the program a little bit better.
It's interesting because it was also the solution that Gynvael chose when playtesting.
Yes, exactly. So it looks like people are a lot more comfortable with probing values on a CPU than they are on a GPU. But what a surprise. But they did use the Lua code. They augmented the Lua code in order to work out if the simulator was correct or not. But they eventually managed to extract a working simulation of the entire program. And they quite quickly worked out that the hardware that was being described within the GPURTL was effectively running one of two potential sort of functions in a Feistel structure, which if you're familiar with cryptography, you know, Feistel structures are a way of creating, see if I can get this right, creating a block cipher from a one-way function. It involves XORing things in 2 blocks. You XOR them and then swap the values a bunch of times for n rounds. And with some further analysis and by using their simulator, they found out what the black box function for each round of the Feistel structure was. They didn't analyze it any further. All that they needed was that function that allows you to implement the Feistel structure. Because with a bit of knowledge, you can use the exact same function to decrypt instead of encrypt because of the way that Feistel structures work. So once they had that black box function, they just wrote a decryptor and decrypted the expected output back into the input without knowing actually what that function did at all. So when I went and chatted to them, they didn't know what algorithm it was. They knew it was an encryption algorithm, but they assumed that it was some sort of custom encryption algorithm. So I gave them a little hint on the actual encryption algorithm in use, the tiny encryption algorithm, and told them, you know, there's reference code on Wikipedia if you want to verify what your thing was doing. But it was really cool to see that they had enough experience with cryptography to recognize the Feistel structure and then realize that you don't actually need to analyze it past that stage. As long as you've got the sort of iteration function, that black box function that they pulled out, then you can implement a decryption algorithm very simply because the key was static by design. Mm-hmm. So the function didn't change with the input. That was to make it easier and also to allow this sort of attack. So really cool how they didn't actually need to reverse the entire algorithm. They just worked out it was a Feistel structure. Here we go. So in the tiny encryption algorithm, the key feeds into how that one-way function actually works. Okay. So they didn't need to care about the key at all. Once they had the function, they could reverse the Feistel structure and just decrypt.
Ah, okay.
So they built a decryptor without knowing the key,
okay,
which is quite cool.
Okay, awesome. Thank you.